Dear students, today we will discuss Buckingham Pi theorem. So let's start. So Buckingham Pi method or theorem, if there are n variables, both dependent and independent variables, in a dimensionally homogeneous equation, and if those variables contain m number of fundamental dimension, then the variables are arranged into n minus m dimensionless term, and those dimensionless terms are called pi terms. So if we take one example in generalize, suppose x1 is a function of x2, x3, x4 so on up to xn. So x depends upon x1, x2, x1 depends upon x2, x3, x4 like that. Then you can write another same equation in that fashion. A function of f1, x1, x2, x3 so on is equal to 0, and each term can be replaced by a term m1, pi 1, pi 2, pi 3 by considering this equation, this formula n minus m. So let's try to understand the step for determining the pi terms. Step for determining the pi terms. Number 1, list all the variables, both independent and dependent, involved in the phenomenon. Let n, small n, be the total number of variables involved in the phenomenon. Number 2, list the fundamental dimension of each variables like capital M, L, T. Let small m be the total number of fundamental variable dimension involved to represent all the variables. Number 3, express the problem in terms of a dimensionless parameters. Here, number of dimensionless parameter will be n minus m. Number 4, identify the repeating variables. The number of repeating variables should be same as the number of fundamental dimension involved to represent all the variables. Number 5, form the pi terms by combining the repeating variable with each of the remaining variables. Number 6, solve the dimensional equation to obtain the dimensionless parameters. Each pi parameter solved by principle of dimensional homogeneity. So let's talk about selection of repeating variables, which is very important. Number 1, m repeating variable must contain all the fundamental dimension involved in the phenomenon. Number 2, repeating variables must not form non-dimensional parameters among themselves, that is, pi terms by themselves. Number 3, as far as possible, the dependent variable should not be selected as a repeating variable. Number 4, no two repeating variables should have same dimension. Number 5, repeating variable should be chosen in such a way that one variable contains geometrical properties like length, height, etc. Another variable contain flow property like velocity, acceleration, etc. And third contain fluid property, mass, density, viscosity of the fluid, etc. So let's take one example. The resistance R experienced by a partially submerged body depends upon the velocity, capital V, length of the body, small l, viscosity of the fluid, that is dynamic viscosity mu, density of the fluid rho, and gravitational acceleration g. obtain a dimensionless expression for R. So this is the problem. So in this problem, resistance R is a function of velocity V, length L, viscosity mu, density rho, gravitational acceleration g. So we can write R is a function of V, small l, mu, rho, g. Or you can write F1 is a function of R, V, L, mu, rho, g is equal to 0. Now let's come to the number of variables. So number of variable here is 1, 2, 3, 4, 5, 6. So number of variable, that is n equal to 6. Let's come to the fundamental dimension. So total number of variables is 6. Here R is represented by m, l, t minus 2. V is the velocity, l, t minus 1. Mu, m, l1, t minus 1. M, l, t l minus 1, t minus 1. Rho, m, l minus 3. G, l, t minus 2. And length L is capital L. So fundamental dimension here are m, l, t. So m is 3. So number of dimensionless pi terms will be n minus m, that is 6 minus 3, it will be 3. So we can rewrite the function f1 in terms of pi. So pi 1, pi 2, pi 3 is equal to 0. So let's come to the selection of repeating variables. Here R is a dependent variable, so should not be selected as a repeating variables. Out of the 5 remaining variables, that is velocity, viscosity, density, length and gravitational acceleration, geometrical property length we select L. From the flow property velocity V is selected and fluid property density is selected. Now your number of pi dimensionless pi term will be 1, 2, 3 and that can be represented by this equation. So pi 1 is L V rho R, pi 2 will be L V rho mu, pi 3 will be L V rho Z. So now we can write this pi 1 is equal to L to the power A1, V to the power B1, rho to the power C1 and R, which is remaining variable. So pi 2 L to the power A2, V to the power B2, rho to the power C2 and mu. Pi 3 L to the power A3, V to the power B3, rho to the power C3 and gravitational acceleration g. So let's consider this first pi term, L to the power A1, V to the power B1, rho to the power C1 and R. Since pi 1 is dimensionless, so I put M0, L0, T0, and for L I am putting L. For velocity it will be L T minus 1 to the power B1. For density it is M L to the power 3 C1, and for R it is M L T minus 2. Now if we apply the principle of homogeneity for left hand side and right hand side, for left hand side and right hand side, you will get, that is for M it will be 0. So here you will get C1 and N1 plus 1. Similarly for L, it will be 0 is equal to A1 plus B1 minus 3C1 plus 1. And for T also, this will be 0. It will be T for minus B1 plus minus, this is minus 2. So from this you are getting C1 is equal to minus 1 and B1 is equal to minus 2. So your A1 is equal to minus B1 plus 3C1 minus 1. If I put the value of C1 B1 here, then situation will be, that is, it will be 2 minus 3 minus 1, so it will be minus 2. So you got the value of A1, C1 and B1. So let's write pi 1 is equal to L minus 2, V minus 2, rho minus 1, and R is 1. So you can rewrite like this way: R divided by L square, V square, rho. Similarly we can do the same thing for pi 2. So L A2, B V V2, rho C2, that is mu. Here it will be M naught, L naught, T naught is equal to, this is capital L A2 for VL minus 1 B2, for rho it is M L minus 3 C2, for mu M L minus 1 T minus 1. So for M, so here it is 0, so it will be 0. 0 will be equal to C2 plus 1. For L, it will be remain 0, so L, this is A2 plus B2 minus 3C2 minus 1. For time T, it will be 0, here power is 0, so here you will get minus B2, here I am getting minus 1. So from this equation you are getting C2 is equal to minus 1, here B2 is equal to minus 1. So here A2 is equal to minus B2 plus C2, 3C2 plus 1. If I put the value of C2 and B2, minus, it will be plus 1, minus 3 plus 1, so it will be minus 1. So I can write this pi 2 term as L minus 1, V minus 1, rho minus 1, and that is mu. Or you can write that is mu L V rho. So let's do the same thing, same process for pi 3. So L A3, B B3, rho C3, and it is gravitational acceleration g. So this is m naught, g naught. So it will be L A3 L T minus 1 B3 M L minus 3 C3 for gravitational L T minus 2, like this. So for M it is 0. It will be here only you get M, so C3. So for L it is 0 A3 plus B3 minus C3 plus 1. For T it is 0 for T minus B3 minus 2. So from this you are getting C3 is 0 and B3 is equal to minus 2. So then A3 will be minus B3 plus 3 C3 plus 1. So if I put the value here for B3 and C3, you will get 2 plus 0 plus 1, it will be 1. So we know the value of A3, B3, C3. So your pi 3 will be L to the power 1, V to the power 2, rho to the power 0, that is Z. Or you can write LZ divided by V square. Or we can write your function f1, that is pi 1, pi 2, pi 3 is equal to 0. Or we can write f1 is r L square. So we can write r, so pi 1 value is r L square V square rho, and pi 2 is mu L V rho, and pi 3 LZ by V square, which is equal to 0. Or you can write r L square V square rho, or you can write is a function of mu L V rho, or L Z by V square. Again we can write r L square V square rho. Suppose this is pi 1, we just interchange this one is L V rho by mu, and this one as a V root over of LZ. So this formula, this L V rho divided by mu is nothing but a Reynolds number, and V root over of LZ is nothing but Froude's number, first number. So we can write your R L square V square rho is a function of Reynolds number and Froude number. So this is your final solution. I hope you understand. Thank you. Stay safe.